In the previous lecture video 6.1 part 1, we already discussed the Lewis structure of ionic compound and also of the covalent bond as well, including the discussion of the formal charge and how to use the formal charge to determine the best Lewis structure. In this video, we are going to focus our attention on the second part of chapter 6.1. We are going to look at the resonance structure. Okay, so what is resonance structure exactly? The resonance structures are the Lewis structure that have the same position of atoms but different position of the electron or the number of bonds between each of those atoms. Again, note that the order of the atom have to be the same, okay, but the difference would be the location of the bonds. Okay, so what do we mean by that? Okay, so let's take a look at an example. So we are going to take a look at the three possible valid Lewis structure that come from N2O. Remember, this is what we focus on here is the resonance, which means you will have to have the same order of atom. So that means in this case, because we have N2 and O, we are going to first count the number of total valence electron first. So 2 nitrogen add to 1 oxygen, total number of valence electron will equal to 16. Okay, and because nitrogen has lower electronegativity value than oxygen, we are going to put nitrogen in the middle. Again, the reason why we do this is because if you remember the formal charge, right, the best central atom would be the atom that have the least electronegativity value. So that's why I'm going to put nitrogen for that. Okay, if you're not sure, okay, so another one that you can also write out would be NON like this, right? And then you will see that this structure here would have a higher formal charge than this type of skeleton. So that's why I'm not going to actually mention about this at all, because eventually this one would be better, right? Because it have the least electronegativity value in the middle. Okay, so what I'm going to do is that I'm going to focus on this skeleton where the nitrogen is in the middle, and what we're going to do is we are going to add the single bond to each of those atoms, right? So between each of those, and you are going to start to count the number of bonding electron. Okay, so the number of bonding here would equal to 4. Okay, so that means you are going to have 12 left to go. When you have 12 electrons left to go, what you can do is you are going to distribute those electrons to the outer element first, right? So not the central, only the outer element. If you do that, you are going to see that this structure is not going to be valid yet because this nitrogen is lacking of octet. Okay, so in order to make this nitrogen to have an octet, you need to start to making these lone pair, turn them into double bond, or sometimes it might be triple bond. Okay, so what I'm going to do is I'm going to pretty much moving these two, right, and make the double bond between those elements. Okay, so I'm making double bond. So now if you do that, you are going to see that we have still, right, total the number of electrons would equal to 16, and each of these elements also contain 8 electrons surround them, so they have an octet. So this would be a valid Lewis structure. Okay, that's one of them. Now you might ask me, hey, wait a second, but we have so many lone pair though. How do you know that you are going to choose those two? What about if I do this, right? And I just choose the two from the nitrogen and make it to be triple bond and I'm not touching oxygen at all? Is that going to be wrong? The answer is no, right? Because of this still have an octet. This has an octet. This also have an octet. This is also have an octet. 1, 2, 3, 4, 5, 6, 7, 8 electron, right? So 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen still have 8 electron. This is 6 electron plus 7 plus 8. So oxygen also have 8 electron as well. And the total number of electrons still come out equal to 16 also, right? If you count, right? So 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So it's still count as 16. So another thing is, well, if we can do triple bond on this side, what about if can we do triple bond between oxygen and nitrogen? Would that be possible? The answer is yeah, right? So that should be possible as well because you still have everything, every element still have an octet and you still not exceed this number of electrons, right? You spend exactly 16 electrons. So that means these three Lewis structures are valid. Okay, when you have valid Lewis structure like this This is what we call resonance structure, because the only thing you change is the location of the electrons or the location of the bond, right? But the order of the atoms still the same. You probably noticed that I did not change the order at all. Again, when we talk about resonance structure, the order have to be the same. The only difference is going to be the location of the electron. So it can be single bond, double bond, triple bond, right? Those are the location that is going to change. Now, since we can write 3 of these, and 3 of these are called resonance structure, you can use this type of arrow to indicate that. Okay, so the double head arrow indicate that these are interchangeable. They are resonance structure of each other, right? They are related. They have the same order of atoms but different location of electron. That's what it's referred to. Okay, so that's the definition of resonance structure. Now, the resonance structure also has the most important structure as well, where the one that is going to contribute most to the correct structure of the compound, right? So you can do that by using the formal charge. Okay, so in you are going to calculate formal charge of nitrogen. Okay, so it's come out equal to -1. How did I get -1? Again, refer to the previous video, right? To calculate formal charge of nitrogen, you need to have the valence electron of nitrogen, which is 5. 5 minus number of lone pair electron, right? So 5 minus 4, right? So it's equal to 1, okay? Minus 2 is equal to -1. Okay, so that's how we get it. Now for nitrogen, 5 valence minus 0 lone pair minus 4 bonds. So that's going to equal to 1, right? Oxygen, 6 valence electron minus 4 lone pairs. That's equal to 2 minus 2 equal to 0. Okay. If you continue doing this, okay, find out all the formal charge for all of these elements. This is what you are going to get. Okay. I highly recommend you to actually try out yourself and check your answer against mine. Okay, so that way you know exactly to just make sure that you actually know how to calculate formal charge. And according to these 3 resonance structure, they are going to be valid Lewis structure. They have the same number of the same order of elements, but different location of electron. So these are going to be the valid structure for this compound. However, one of them would be the most important, which is going to contribute most to the correct structure. That is going to be the one that is going to fall into how we talk about how formal charge can be used to find out the best structure, the best represent structure, right? So as we mentioned in the previous video. So in this case, what you are going to do is that you are going to look for the structure that have the formal charge that come out close to 0, right? So in this case, what we can ignore would be the last one, because this one, the formal charge, is not as close to 0 as these 2. Okay, so that means we can actually eliminate this, right? So this is probably be the least important structure. Okay, it's still valid, but it's the least important. Okay, now between these 2, which one would be the most important structure then? Okay, so the most important structure would be not only the formal charge that is equal to 0. If you end up having a negative formal charge, the negative formal charge need to be on the atom that have the most electronegative atom, because the most electronegative atom indicate that it's most likely to withdraw electrons. Therefore, their formal charge need to be a negative value. So in this case, between if I go back here, so this is the review from the previous chapter, right? So previous lecture video part 1, okay, page 98, right? So there are 2 criteria that we are looking at here. Okay, so pretty much if you're looking at between nitrogen and oxygen, oxygen has higher electronegativity value than nitrogen. Therefore, in this case, you are going to have this structure to be the most important one, because the negative formal charge is on the most electronegative atom. Okay, so that's why this structure right here would be the most important. Okay, it's more important than this one. Okay, and this one is more important than this one. Okay. Again, to recall from the previous lecture video is that when you are calculating for formal charge for all atoms within the molecule, you need to make sure that you check your answer as well. The summation of the formal charge for the neutral molecule, this is neutral, when you add them up, is need to equal to 0. Okay, so this is neutral molecule, add them up is need to equal to 0. This is neutral molecule also, right? Add them up, it need to equal to 0, so that's good, right? After you check your formal charge calculation, the next thing is to find which one that have the formal charge closest to the 0, and we already say that it's these two, right? And because these two, the only thing is different is the location of the formal charge right now. So you are going to use the negative formal charge to be on the most electronegative atom, which is oxygen. So that's why this is the most important structure. Okay. All right, so let's take a look at the second example, which is the resonance structure of sulfate ion. Okay, so we are going to draw these, and we're also going to calculate for the formal charge and find out which one is going to be the most important structure as well. Okay, so sulfate ion. Okay, so the word ion means it have to have charge, right? So this is sulfate is going to be one of the polyatomic ions. So this is the formula of sulfate ion. So SO4 2 minus. Okay. So clearly, right, so if you look up the periodic table, the electronegativity value, you will see that sulfur has lower En value than oxygen, and also there is only one sulfur here, so we can put sulfur as the central atom. Okay, so but before we do that, let's count the number of total valence electron first. Okay, so again, 6 come from sulfur, 4 times 6 come from the valence electron of oxygen, and 2 minus indicate that these ion accepting 2 electron, therefore you need to add 2 electron at the end. Total will come out equal to 32 electrons. Okay. After that, then you are going to put skeleton, right? So as you see, sulfur has lower En value than oxygen, therefore sulfur would be in the middle. And what we're going to do is we're going to start with single bond. Okay. If you start with single bond here, you are going to end up using 8 sharing electron total. If you subtract that from 32, you are going to have 24 electron left. If you have 24 electron left, what do we do? Well, we already say, right, we are always going to distribute these 24 electron into each of those outer or terminal atoms. So in this case, I'm going to distribute those. Okay, 24 divided by 4, that's 6, right? So you can add 6 electron around oxygen, and also it's making oxygen to have an octet too. So according to this structure, it seems to be valid, right? Because if you think about it, oxygen contain what? 6 electron, 6 what do you call lone pair electron, and plus 2 electron from the bonding. So this is equal to 8, right? Sulfur contain 8 electron as well around the sulfur, so it does seem to be valid. So this structure is the valid Lewis structure. Now, after you're done with the Lewis structure, you need to put a bracket with the superscript 2 because this is the ion. Okay, so we need to indicate that the overall charge of this is equal to -2. Okay. If you calculate the formal charge, you will get -1 for oxygen because oxygen has 6 valence electron, 6 minus 6 of the lone pair electrons, right? And then -1 is equal to -1. Okay, so all of this is -1. And if you do it the same for sulfur, sulfur has 6 valence minus 4 bonds, no lone pair electron. So therefore, it's going to be 6 minus 4 is equal to 2, right? +2. So you probably notice that this structure is actually not quite good because the formal charge is not close to 0, right? You have -1 and you have +2. This is not close to 0. We want each of those elements to have as close as to 0 as possible. Okay, so that means in this case, this structure right here, yes, is valid Lewis structure, but it's just not what do you call, like, it's just not it's not the most important one yet. Okay, because the formal charge is not close to 0 yet. Note that because these ions, the overall charge is -2, therefore when you calculate the formal charge for each atom, when you add all of them up together, like add these together, you are going to end up with -2 as well. Okay, so that's how you check your calculation for formal charge. Okay, so what can I do? Okay, so what if I put double bond right here between oxygen and sulfur? Okay, so by changing these two electron right here and move it to double bond, right? So what would happen? Okay, so if I do that, so I'm going to pretty much get rid of these two and put it as the double bond, right? So if I do this, what you can do is calculate the formal charge again. Of course, formal charge of these three oxygen will still the same, right? Because we did not change them. The only two that change would be oxygen and sulfur. If I do this, you are going to get, so for oxygen, you have 6 valence, right? 6 minus 4, that's 2. 2 minus 2 is equal to 0, okay? If you do it for sulfur, sulfur has 6 electron, right? So 6 valence electron minus 1, 2, 3, 4, 5. 6 minus 5, that's equal to positive 1. Okay, so, okay, it's getting better, right? Because it's getting closer to 0. Okay, we want the formal charge to get closer to 0. So, but wait a second, what about the sulfur though? So oxygen, clearly all of these have an octet. 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8. What about sulfur? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that possible to have for sulfurs to have 10 electrons? This is going to be the exception that you are going to learn in part 3, okay, of this chapter 6.1. Okay, so just wait for me here. So sulfur would be one of the elements that would be the exception that you're going to learn. So in this case, just know that it is possible for sulfur to have more than an octet. We're going to talk about that later. Okay. What if I add more of double bond right here between oxygen and sulfur? Is that going to be like still it's going to make formal charge better or not? So we can do that as well, right? So you are pretty much moving this, right, to make it to be a double bond. Okay, so if you do that, you calculate the formal charge again, you are going to get -1 the same, right? Since you already calculate formal charge to oxygen with double bond and 2 lone pairs, so those are going to be the same, right? 0 and 0. For sulfur, then it's going to be what? 6 minus 1, 2, 3, 4, 5, 6. So that's also equal to 0 as well. Okay, so that's good, right? It's getting closer and closer to 0. What if I just keep adding it? Okay, so if I keep adding double bond and calculate formal charge, okay, so this is what you are going to get. Okay, last one. Okay, so if I choose double bond for all, right, so is that going to make it even better? So let's take a look at that, right? So -2. Okay, so now which one should be the best Lewis structure though, or the most important? Okay, the most important Lewis structure need to have the formal charge for each atom closest to 0. Okay, we can eliminate this one because it's not close to 0. This is not going to be the most important one. Now between, so the second one clearly, right, so this has a lot of 0, right? This has just 1 0, so we can also eliminate this one as well. Okay. Now what about this one? It have a lot of 0 as well, but -2 here. You see that sulfur -2 is way off that from closest to 0, so we can also ignore these two. Okay, because the -2 is not close to 0. So that means the two structures that are the best candidates so far is these two. Okay, these two, or the atom has the formal charge closest to 0, right? So we have 3, 0, and we have -1 that is closer to 0 than -2 here, right? So now which one is better? That is when you would need to look up the electronegativity again, and you want the formal charge, the negative formal charge, to be on the most electronegative atom, and that is going to be on oxygen instead of on sulfur. So therefore, in this case, this would be the most important structure for sulfate Lewis structure. But these 5 of them are the resonance structure of each other. Okay, so this again is the exception. It's called expanded octet. Expanded mean is more than or exceeding an octet, right? We're gonna learn this a little bit more in the next video, why sulfur can accommodate more than 8 electrons. Okay, so we're gonna talk about that later. But know that in this case, the reason why we choose this structure because the formal charge is closest to 0, and also the negative formal charge is on the most electronegative atom. Okay, so this is the most important. Okay. So now I'm going to choose this most important here. You probably notice that hey, wait a second, if I choose this, what about the location of double bond? Can I change those as long as I have it as equal to 2 double bond? The answer is yes, right? So what we can do is we're gonna take this most important one, okay? These are not important because the formal charge is not close to 0, right? It's the least important compared to this one. We are going to focus on the most important one, and we are going to focus it on even further, right, with more detail. What we're going to do with this is that I'm going to change the location of the double bond, right? So I'm just going to change from this one to this one, right? So as you see here, another one is changing from this one here, right? This one here down here, right? So as you see, and also this one stay the same, right? Okay, so that's what I'm changing right now. If you do that and you also calculate the formal charge as well, you will see that they are equally important because they all have the formal charge closest to 0, and the negative formal charge still on the most electronegative atom. So that means all these three are equally important. Okay, one is not better than the other. They are equally important. Okay, not the same as what we see before. These are not equally important. Okay, because the formal charge is not close to 0 and the negative formal charge is not on the most electronegative atom, right? So we are choosing this most important one, and we are going to go further, and we see that of these three that we just changed the location of the double bond, those are equally important. Okay, because they are equally important, so how can we describe the actual structure of sulfate then? That's when we will need to get the average structure, which is what we're gonna call resonance hybrid. Okay, because when you're having the resonance structure that are equally important, okay, in nature, they are going to present in these three forms equally. So therefore, it's going to be present as the what do you call, like, the average structure for that, right? So we call that hybrid structure, hybrid resonance structure. This is similar to, if you think about this in terms of like horse and donkey, right? So let's say like these two are resonant of each other, right? They are equally important, right? The average of these two, that is going to be the actual structure of the molecule, is the average representative from the two equally important structure, right? It's going to be represented as the hybrid structure. So in this case, mu would be the resonant hybrid of these two. That's what it kind of like, that's the analogy of it. Okay, so similar to this, okay, so I'm going to give you more the definition here. So pretty much resonant hybrid is going to be when you have two or more resonance structure that are equally important, right, or the correct one, and the actual structure would be the average of those equally important resonance structure. For example, this is the Lewis structure of nitrate. Okay, so this is the most important one. Okay, and if you move the double bond to the other side, right, this is also equally important too, because all you do is just change the double bond. So that means the formal charge should still stay the same, right? If you also change the double bond to this oxygen right here, right, they all are pretty much the same. It's just change the location of those double bonds. So these three are going to be equally important. Okay, and the reason for that is because, again, you can calculate for formal charge, and you will see that they all have the, what do you call it, closer to 0. Okay, so, and also the negative electronegativity, the negative formal charge is on the most electronegative atom as well, right? So in this case, all of these three are equally important, okay, because they are pretty much almost the same. So if you get the average of this, so how do you get the average? So pretty much note that there is the movement of the double bond. That's indicate that the double bond can move around. So we are going to just indicate that by like dot 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 here, indicate that this is can moving around. Okay, so this would represent the true actual structure of nitrate, which is going to be represented by the resonant hybrid, okay, which is the average structure. Note that on the exam, if I ask you to draw the resonance structure of nitrate, you need to give me 3 of these. Don't give me the hybrid, okay? So this average right here is called hybrid structure. If I don't ask for resonance hybrid, do not give me this structure. Most of the time, give me the actual resonance structure or actual Lewis structure for that. Okay, so again, if you think of this as horse, donkey, and mule, right? So the resonance structure that are equally important, right? The average of that would be the true representation of that, right? Which is the is expressed by resonant hybrid. Okay. All right. So up until this point, you should be able to start working on paper homework 6.1 part C. Okay, number 6, 7, 8. Okay, so 6, 7, and 8. So you should be able to start working on those now. So for number 6, okay, so that is the hint here. You are going to provide 3 resonance structure for each of the following. Again, when we talk about resonance structure, right, you are going to have the same order of element, but different location of bonds or electron. Therefore, in this case, if you're looking at this, right, think about the previous problem, which is problem number 4. Okay, problem number 4 and actually 5 as well actually walk you through how to choose central atom, right? So pretty much number 4 and 5 will teach you that. Okay, so according to that, right, so you should be able to find out which one should be the best central atom, as we already discussed, right? The one that have the least electronegativity value would be the central atom, according to, you know, like the formal chart that we probably did on the number 4. So in this case, you probably see that for SCN, it would be in that order. NO2, N would be in the middle, and 2O would be outside, right? So those would be the order. And you are not going to change the order because we are drawing resonance structure, 3 of them. So that means you are going to do 3 times of this, right? Except you are going to have different type of bond between each of those elements. Okay, so that's what I'm looking for, right? So all of these would be resonance structure, but you just need to find out what do you call, like the type bond between each of those, and you're going to have to like move them around. Okay, and then you are going to calculate formal charge. Okay, and then find out which one would be the most important structure. Okay, so again, don't just circle the most important, but also briefly explain it to me as well. So 2 criteria, right? One is formal charge must be close to 0. Second one is the negative formal charge have to be on the most electronegative atom. Okay, so you can do that. All right, so the review for this video would be this part right here. We talk about Lewis structure, right? We talk about resonance structure, and we look at the formal charge of each of the elements, and we use the formal charge to determine the most important structure, right? And if you have 2 or more most important structure, right, that they are equally important, you can represent them in the actual in reality, the actual molecule would be represented by the hybrid structure, which is the average of all of those. Okay, so again, don't forget to start working on homework part 2. And as I mentioned earlier, part 4 and 5, the difference between 6 and 7 would be 4 and 5 asking. So 4 is actually asking for you to draw the structure with different central atom. Okay, so in this case, number 4 for SCN, it would be SCN, right? Or NSC, or what? SNC, right? So those are different central atom. And according to this number 4, whichever one that is the best Lewis structure, you are going to have to tell me which element is the best central atom, right? Because that best central atom will then can be determine your part 2, right? Because in part 2, you are going to have resonance structure which have the same order of element, okay, but different location of bonds. So that means in this case, one of these is the most important. It would be, you're gonna start it right here, right? So for example, if carbon is the best, so SCN, you are going to do SCN. You are going to do SCN, exactly what we mentioned earlier, but 3 times with different location of bonds, as I mentioned earlier. Okay, so those are different part. Okay, so the goal for these 2 are not the same. Okay, so you still need to actually understand that a little bit better. Okay. All right, so again, number 4 and 5 will help you understand more why a certain atom is better be in the center of the molecule. 6, 7, 8 will tell you about the resonance structure, which is going to be the location of the bonds are different, but the order of the element will still be the same.